This is Ted Robinson doing the high-powered magnetic loop antennas. I'm an old guy who fixes radios and done 20 years of urban hamming. So I've done a few magnetic loops. Now, is it good for you? Are you in a city lot with wires and houses and trees? No place for a ground system? No room or height for a dipole? Well, magnetic loop is 1/10 the size of a dipole, but 10 times the cost. Now, stepper tuning is a huge breakthrough that's made it much more practical. And, we'll see. We'll get into the physics of a magnetic loop antenna. The small antennas generally have loading coils, OBL whips, dipoles, and they have a Q of about 300. Magnetic loop is loaded with a capacitor, Q of 5,000, which right there is a step up. Good example is the highway advisory antennas at around 1700 kilohertz. They're limited to a 10-foot diameter, 10-foot size, and typically it's a vertical loaded with a ground plane 10 feet. Efficiency a little less than 1%. If you take a 10-foot diameter 4-turn loop, you can get 8%. So it's definitely pays. In addition to being more efficient, going from the conductor to the near space, when you go to the far field, there's a difference as well. Magnetic loop starts with a magnetic field, and when it hits the ground or wiring or trees, the reflections that it induces are in phase with the original wavefront. So the loss is very little. Dipole has an electric field, has two verticals, and when they reflect off of trees and house wiring and the ground, the reflection's out of phase and you get loss. Good example of this, W1LYQ, he wrote an article in Q Street, and he had a 20-foot loop on the ground, and his signal was as good as the signals from dipoles in the States all over the years. And we're talking 275-foot, 160-meter dipoles, 50 feet in the air. He had a little 20-foot loop on the ground. And that gives you an idea of how that works out. Now, as I mentioned earlier, tuning is the big pain in the neck. You go 4 kilocycles on a 20-meter band, and you're a 2-to-1 SWR on the 75-meter band. Luckily, robotics people have made stepper tuning now pretty much a plug-and-play affair. And it's a good thing, because tuning was the #1 EHAM complaint. DC motors go right past the sweet spot there. Now, it is, you do have to adjust the tuning every time you QSY, but the good side is that narrow bandwidth is like a roofing filter for your receiver. Keeps out the heavy QRM down the band and broadcasters. And you can run an amp in the city, because those harmonics and the spurious stuff also get snuffed out by the narrow bandwidth of the antenna. And in addition, the coax is matched at the antenna. So the coax has a flat SWR, which means it picks up very little, and it also radiates very little. So it's amazing what you can get away with. Now, efficiency versus weight is another design thing that you want to look at, because the radiation resistance of a magnetic loop goes as the area squared. And the area goes as the perimeter or the diameter squared. So that's a fourth power relationship between size and radiation resistance. And of course, the ohmic resistance of the loop goes as the size. So there's a very steep curve when you get in the small sizes, but when you get up towards 100% efficiency, of course, it doesn't increase as rapidly. There's a knee in the curve. And that knee is the sweet spot where you're going to have right around 1/6 wavelength perimeter. Efficiency is right around 50%. Double the size, you'll only gain 2 dB. Cut it in half, you lose 7. Here's the curve here. Shows you the situation. You can see that right around 0.04 is your sweet spot. And this is a round corner square made out of 3/4 inch copper tubing. And 0.04 on the side, that's about 1/6 of a wavelength on the total length of the tube you want. And that works out to roughly in feet, about half of the wavelength in meters. So 80-meter band, 40-foot piece of tubing will do you. Here's one. Here's what 40 feet looks like in the sky. Current design tunes 2 to 8 megahertz. Notice it's a square shape, not a round shape. That's another design choice that seems to make sense, because if you're in a limited space, and that's what the magnetic loop is for, you got you're on a balcony, say, or a porch. The width of the antenna is crucial. And if you have say a 1.5 to 1 rectangle where the narrow side is horizontal, you can get almost twice the area compared with a circle of the same width. And of course, area is what you want. Anyway, the other design choice you see in this picture is those things hanging down on the bottom. Those are doorknob capacitors tied directly to the ends of the tuning capacitor. And it's 6 feet in the air. It looks like it's higher in this picture, but it's only 6 feet in the air. Here's a detail of it. Look at those ugly little doorknobs with straps in between and alligator clamps to the coax. You get on a step stool and you can change bands in a jiffy. I generally find these, you need 6 kV doorknobs, and because you're looking at 10 or 15 kV across that big capacitor up there to run a kilowatt. And the string of capacitances going down each side allows you to select different coupling capacitance values depending on your frequency. Now, conventional loop, such as the one in our logo with a gamma match, or the little loop, the little 1/5 size loop, those two matching setups are at the opposite side from the capacitor, which means the coax would have to go to the top of this particular tree hung antenna. And if you wanted to change bands, you'd have to lower the antenna completely. Anyway, that 80-meter antenna is tuned by a 500 picofarad vacuum variable. Here's another detail on the construction showing how the motor, which is at the top of the picture, is separated from the capacitor by about 8 inches. That motor is at ground potential, and you don't want anything at ground potential near one side of the loop versus the other. The second side of the loop is at the very bottom of the picture, and where the 2 bolts are into the capacitor. And you can see the flattened copper tubing and the doorknob capacitor attachment in that particular one. Now, this motor is a NEMA 17 bipolar stepper. And we'll get into that in the construction details. The last frame will have that for you, and so that you can order the darn thing. Anyway, these are the things to remember. You have to bend the tubing carefully so you don't kink it. And you don't want to over tighten the screws and the capacitors. And suppliers, eBay is by far the most plentiful supplier. That's where you're going to get your copper tubing and your quadrature. Now, this is another thing you want to keep this slide for. 200 pulses per turn, quadrature, rotary encoder. That's your search term for eBay. And you get it out of China Tool or one of the other suppliers there. Doorknob capacitors, 39 picofarads is a good value. Get 6 or 8 of them. You might even want to get 1 or 2 33 picofarads or 47 picofarads, mix them up. And the vacuum variable, 15,000 volts. Now they come in 2 flavors. You got the ceramic kind that have a nice flange where you can attach everything, the tubing, the doorknob capacitors, and the motor mount. Or you can get the old Soviet kind, the glass with the knobs, in which case you're going to have to put a strap on the knobs and then drill a strap for attaching all that other stuff. And pololu.com is your supplier. Again, that's polo like a polo pony and Lu like half of Lulu. And the stepper motor driver is a TIC T500. And the motor that I use, it works out really well, is a NEMA 17 stepper motor, and it's their part number 1200. And you're going to download software. Actually, yeah, you're going to download software that presents a screen, and you're going to be filling in various values that are not too hard to suss out what they are. One of the things you're going to look at is they're going to ask for the current that you're going to put into the motor. And the way I approach that is you have a certain torque that'll turn the capacitor, and then there's a certain torque that'll break the capacitor, which is many times as great. And when you set torque and the set amperage in the TIC software, that will determine the torque. And you can turn your motor against that torque and feel whether or not you've got too much torque or not enough. The other thing that you want to be careful of with the motor is it makes a big racket on receive. So have a knife switch so you can depower your stepper when you're receiving. When you're operating, you have that MFJ antenna analyzer to get resonance and matching. And you can check the Q for maintaining efficiency. And the Q is simply a matter of how far apart are the 2.5 to 1 SWR points. If they're, say, 8 kilocycles apart, at 4 megacycles, you've got a Q of 500. And if all of a sudden they become 16 kilocycles apart, then you know something's gotten loose and it's time to go out and check the tightness of your connections on the antenna. Construction details here. Not a whole lot more to add. It's all pretty much mundane stuff. You order your copper tubing from eBay and get your little doorknob capacitors as well. And then the rest of it you can get in the hardware store as you need it. Now, what are the future possibilities? Well, I've done some experiments already, and I've actually gotten some gain in front to back at 20 meters with these two 4-foot loops. So there's a possibility that we can have a mag loop Yagi. And of course, there's also the possibility of a mag loop 4-square. Anyway, time for questions.
All right. Welcome, everybody. I'm Paul Topolsky, W1SEX, and I'm introducing Ted Robinson, K1QAR from Boston area. And let's see what we've got in the chat here for some questions. Holy cow already. All right. And so let's see from Patrick, how do we perform indoors? How do they perform indoors? And lives in an apartment without a balcony. Go ahead, Ted.
Well, I had one in a metal hanger and talked to a fellow from France with it on 20 meters. So they do surprisingly well indoors. Of course, if you're going to run a kilowatt, you do need to beware of the distance, safe distance to stay away from it. So try to put it at the other end of the room if you're going to run some power. So that's the indoor question. And down at the bottom, I see the HOA. Yeah, you can put the thing on a tripod in the yard and see if they yell at you. It's temporary. And generally speaking, temporary stuff is not subject to the same rigor in the regulations as something that's bolted into the side of the house. I'd say it's a good candidate for a homeowners association antenna because it's small, and the rest of it's all about that logo that kind of surprised us when we saw that.
Yeah. Well, there you go. How about the remote switch used to switch doorknob capacitors in and out?
I just use alligator clips. I get up on a step stool and switch them because I don't switch bands that often, but obviously you're only switching the coax, so you don't have to have a fancy switch. Like if you were going to switch capacitors that are directly across the two ends of the loop, then you'd have to worry about how many milliohms. But for the doorknobs, yeah, regular relay setup would work just fine.
Okay. And next question about already got a stepper controlled variable. Why do the doorknobs at all? I take it that's to extend the range of the antenna.
Well, there's two aspects to the antenna. There's one resonating the antenna, which is very particular. It's a very narrow resonance point, and that's what you need the stepper for. And the other is once you get the loop resonant, you need to feed it with a 50 ohm piece of coax. And as near as I can tell, you're looking at somewhere around 1,000 ohms feed point at the tuning capacitor, either side of the tuning capacitor. At the higher frequency range, the impedance is maybe 2,000, and down at the minimum frequency, you might be down around 750. So that's why you have to change out the doorknob capacitors to make 50 ohms turn into 750 or maybe 2,000.
Right. And a question about feeding with 50 ohm or open wire. Can we feed them with open wire?
I've never tried that. You might need a whole lot less capacitance or no capacitance at all. It's an experiment that someone else can try. I like the coax because it's convenient. And once you're bothering with the capacitance, or some kind of a matching setup, you may as well go with the simplest, easiest feed line because coax, you can just lay it on the ground, lay it on the floor, and open wire, you gotta, and when it ices up, that's I don't know what open wire does. I don't mess with that stuff.
Okay. All right. And what about the loop conductor, conductivity, copper tube, coax wire, et cetera, at high power?
Um, I think a coax shield is probably very close to a copper tubing. The only difference is the coax is floppy, so you need a frame. Being lazy, I like the tubing.
Yeah.
Some of the coax shield, I think, is it waves in and out, but I don't quite understand that either. But the path length is, of course, you want as short as possible because that keeps the resistance down.
Yeah. Our discussion before the show here, I'm planning on building one using hardline, and that would certainly take out uh, any questions about the shield giving us a hard time. So, because that's a continuous shield. All right. Let's see here. What about capacitor spacing? And again, we had that discussion before the thing. If you're not using a variable capacitor.
Yeah, I think there's it's in air. Air dielectric is so many volts per so many millimeters. It's. I don't know offhand because I don't use those capacitors, but it should be a simple matter of Googling and whatever the spacing you've got in your capacitor, you should be able to determine how many volts it'll stand. And of course, watch that SWR meter, and if it starts to wiggle, you start getting a lot of reflected power. Back off quick because arcing in a bread slicer, um, a capacitor that has plates, it degrades it rather quickly.
Yeah, we were talking about something like this would probably handle 100 watts easily, so that should handle that. You want to go above higher power, you're going to have to either increase the size of the capacitor itself or go to the vacuum variable at 15 kV. All right, let's see. Does a reduction of antenna size in a loop severely decrease receive signal sensitivity?
Well, I think that receive signal sensitivity is in two parts. It's signal to noise as well as the absolute signal strength. So obviously you're going to get absolute signal strength reduction in proportion to the area, but you also get noise reduction so that your overall performance maybe does not degrade as severely as transmit performance would degrade.
Okay. Go here, and we're talking about motorizing the unit. Is there a simpler way than the uh, stepper motors?
You can use a regular old DC motor, but I found that they're problematical. And, when you get all done with the transmitter and hanging the antenna and, everything else that has to do with the ham station, the addition of a motor doesn't add that much to the overall package, either cost or time wise. So I haven't really found a simpler way to remote the thing, other than if you're just going to work on one frequency for a net, then you probably don't need a motor. You can tune it by hand, standing next to it with and one of those MFJs, and once you get it set, you just leave it. But if you're going to go cruising on the bands, I think a motor is by far the easiest way to go.
Yeah, I think this was a 0.6 RPM motor that I'm going to put into my project here, and it's a simple reversal, but it does come with with this one. It comes with a controller, and that would be 0.6 RPM as a high speed. So I'd be able to slow it down with the controller, and hopefully make that tuning fine. But again, this is an experiment that I haven't even started yet. So that would be simpler. And this was pretty cheap. I think the motor and the controller was somewhere around $40. So that's a possibility. And I'll let you know how it goes when I get around to building the project. But the stepper motor is far more precise, right, Ken? Yeah, right. Yeah, Ted.
Yeah, I use DC motors and the switching back and forth and going and you miss the narrow sweet spot there with the SWR of resonance. So when I got the stepper motor, I kind of went hallelujah. And what do we got down here?
Okay, I determine when the stepper motor is turned to the end of the and stops. Yeah, that's interesting with a variable cap. They go to one end and they're done.
Well, that's why I talk about the setting the current in between the limit of actually moving the capacitor and the limit of breaking the capacitor. And that way you don't have to worry so much. If it hits the end, you'll notice that your SWR needle will move when you're tuning. And when it stops moving, then you're not going to get any more, when the capacitor hits the end stop, the SWR needle stops moving. So that's how you can tell. And of course, at the maximum capacitance, which is the minimum frequency end, the motor will keep turning because what it'll do, if it's a vacuum variable, it'll actually unscrew the little driver inside the capacitor. So when you discover that and you go back to reverse, nothing's going to happen for a while till it screws that thing back in. And then once it gets screwed back in, it'll start moving the capacitor and you'll see the SWR needle start moving.
All right. Or primarily listen in the receiver first, get maximum noise, then go ahead and fine tune it.
Yep. Now you can do it that way, although with the stepper motor, it makes a racket. You do have to switch the thing off. And sometimes you can hear the racket going up and down, but sometimes you can't. That's a tough one. I prefer to tune while transmitting it at low power.
Okay.
And interesting. The exposure limit.
Yeah.
Good question.
Yeah, that is.
I had a 160 meter loop, and I was running a kilowatt. And I think it might be in the QRZ page. It's an old one. That was a long time ago. It got written up in Antennex. There's pictures of it in there back in June of, I forget what, 2012 or something. It was a long time ago. And that thing, that was when they first came out with, you got to have, if you're running a kilowatt, you got to have, you got to figure out what your safe distance is, exposure limit. Turned out to be 30 feet for a kilowatt at 160 meters. And for comparison purposes, the same power into a dipole, you only had to be 1 foot away. So that is a good question. And you do have to, because it's a small antenna with a lot of power, you do have to give it some room.
Hey, well, we just don't know exactly how much. So if you play
30
it smart,
to 1.
I guess. 30 to 1?
I would just, whatever it is for a dipole for the power you're running, just multiply by 30.
Okay.
You can ask the ARRL. The ARRL had a fellow there that actually calculated it out for me for that one case.
Oh, okay. That sounds good. So get it off to the lab or to your local technical coordinator who will advance it to the lab for you.
And there's the knife switch question.
Yep.
The stepper, and I tried all sorts of little toroids and capacitors to try and shut that son of a gun up, and it did not work. The only way to work it is once the stepper gets you where you want to go, take the power off it. And that's where the knife switch is. Just take the 12 volts off the stepper, and then you can hear.
Yep. All right.
Good question. Another good one. It's got a very, if a magnetic loop were a wheel, the direction of the axle in both directions is a very deep null. I had a 4-footer, and I put a lot of capacitance, and I was listening on the AM band. and I could get 50 dBs of null. But the smaller the loop, and of course 4 feet in the broadcast band is tiny, way too tiny for transmit. That you get you 50 dB, but you can get a good 10 or 20 dB with the transmit and loop. And the pattern that the pattern is going to affect, if you get the thing hanging like mine usually do, like an earring, it's going to affect terrestrial noise sources. So you get the thing oriented to null out the street light or the transformer that's making a racket, and you can just tie it off in that direction. Don't need a rotor. And the skywave, 70 meters, 80 meters, those 75 meters or 20 meters even, skywave 30 degrees or more above the horizon, it's pretty much omnidirectional.
All right.
The air capacitors, yep. You could use it. You can use air capacitors, but usually I like the vacuum capacitors because it's 10 turns, which gives you some more vernier and allows you to spread that null out over a larger turning radius. And in the I leave mine out in the rain, and air capacitors don't like the rain.
Yeah, that's for sure.
Let's see. Coupling loop versus the gamma match. They all seem to work. The test that I do is throw a kilowatt of carrier for about 3 or 4 minutes, and then go out and see if anything gets hot. And nothing gets hot, so they all work. It's just a matter of where you want the feed line compared to where you want to have the control line driving the motor. And if they come off the loop in the same place, it's considerably more convenient in the practical installation situations that I encounter.
All right. Very good. We are at the end of the questions. Any more? Go ahead and get them typed in now before we head out.
Yeah.
All right. So I've heard you on 75 meters on the Sunday morning nets on occasion using your loop. You using usually 100 watts or got an amplifier on it, Ted?
Oh, I got a 500 watt amplifier. My kilowatts on the fritz. It blew some resistors, and I killed a meter the other day trying to fix it.
All right.
MLA design. Boy, that's a good question. Another good one. What's my favorite calculator? I think Pacific 66 has got a good one.
Yeah, I like them guys.
There was another one, and I can't find it on the web anymore. Back 10 years ago, that would actually factor in the ground loss from the magnetic field and the ground loss from the voltage field, the electric field, as well as some other stuff. But as far as the main thing, which is to suss out how big you need it to be, Pacific 66 will do the job.
There you go. And there's my favorite calculator.
Oh, there we go.
50-year-old calculator. Let's see.
That's a beauty.
Coming in here. All right. That's what I use. Okay. Yep. Jamie. Yeah. So very good. Yeah. Pacific 66. There's a whole bunch of good ones out there for all kinds of stuff. We teach technician, general, and extra class classes via Zoom, and we use those quite a bit to do the calculations. So, all right, what else we got here? Your contact info. Well, there we go. Where did it go, Ted? We had your contact.
That's right. Look at that.
Look at that. Our names are, I know what it is.
Well, if all else fails,
yeah,
the simplest one is to QRZ my call.
There we go. Look at that. Get rid of the questions and we're back. So ted.robinson@gmail.com. So there you are.
So anybody else has questions, I'll answer them in the fullness of time. Thanks for tuning in.
All right. Thanks, everybody, and I hope you enjoy the rest of the QSO Today Virtual Ham Expo. And We'll see you. I'll be again tomorrow if they're with Greg, WA1GXR, talking about the Nano VNA. And Greg is the technical coordinator for Western Mass. He's my boss. So hope to see you there. 73, everybody. Take it easy, Ted.
Yep. So long. And sorry I plugged the MFJ
Yeah, that's all right. Nothing wrong with that.
competition.
All right. Take it easy. Bye bye, everybody. 73.
So long.